you can factorize it as half of ue cubed times d theta star dx plus taking derivative of ue, that is going to be 3 ue squared over 2 times theta star times due dx. That is equal to my d, right? Okay, so that is going to give you an evolution of the kinetic energy thickness. That is equal to 2d over ue cubed minus 3 times theta star over ue times due dx. So this gives us an equation for the kinetic energy thickness. And we already have an equation for the momentum thickness, right? That is evolving also with two terms. One term is the tau, is the skin friction, right? So we have the I think one term with CF over 2, and the other term I think is 2 theta plus delta star times due dx over ue, right? Okay, so now we have these two equations. These two equations are going to give us evolution of theta star and theta. And now from the ratio of theta star and theta, we are going to know what's called the kinetic energy shape factor. So this kinetic energy shape factor is very strongly correlated with h, which means that it can be modeled as a function of h. And then we already know that CF can be modeled as a function of h, right? CF is equal to, I think, is a function of, so T can be modeled as a function of h, and T is defined as a CF scaled with the thickness, the momentum thickness of the boundary layer. So it's scaled with, I think theta has to be divided, and I think you have a nu and ue, right? So this is like a 1 over Reynolds number based on theta. So we have h star modeled as a function of h. We have CF modeled as a function of h. And in the same way, the dissipation d can also be modeled as a function of h. So first, let's non-dimensionalize it. So let's it is going to be non-dimensionalized with respect to ue cubed, right? So d is going to be equal to 2. It's going to be equal to a non-dimensionalized version of ue, which is ue to the cube times a cd, a dissipation coefficient. Okay, because if you look at the definition of d, if you scale, right, if you scale ue, it is going to be scaled in what way? So yeah, if you scale ue, that seems to be scaling as a u squared, which doesn't make sense here. There has to be also nu involved. So
tau xy is mu du by d.
So tau xy is equal to nu times du dy. So the dissipation coefficient can be modeled as, so this is mu, right? So the and with the 1 over rho, it can be modeled as a nu times du dy squared dy. Okay, so let's see. You keep nu and scale scale u is actually going to scale like squared. Right, but the dissipation coefficient is actually scaled with ue to the cube. So where does the cube come from?
How is CD defined?
How is CD defined? So CD is defined as this, d over ue to the cube. Right. So let's take a look at the dimension to make sure we are actually doing the right thing. So nu is of dimension L square over T, right? And the du dy is scaled as 1 over T. So it's 1 over T squared. And then this whole thing is integrated over y. So this is times L.
Right.
So the dimension is correct. The dimension is a velocity to the cube power. Right. So the dimension is correct. So that means CD cannot be expected to scale. CD cannot be expected to be just a function of h. This is because if you scale UE, it only the dissipation only scales if you keep nu and scale UE. D scales like UE squared. So CD, which is divided by UE cube, would scale like 1 over UE. Right? So fix my kinematic viscosity. CD is going to be like 1 over UE. And also, if you change the thickness of the boundary layer, so if you keep the same profile, similarity profile, and scale theta, scale the thickness of the boundary layer, how is the dissipation going to change? So we know that the dissipation coefficient scales inversely proportional to UE, and if you increase the thickness, du dy, if you keep the same UE, just to change the thickness, increase the thickness by a factor of 2, how is du dy going to change? It's going to become a half. Now, and you are also integrating over the thickness of the boundary layer. So the whole dissipation would be half, right? Because the du dy squared would become a quarter, and integrating over twice the thickness would be a half. So that means if you increase the thickness by a factor of 2, d and also CD would decrease by a factor of 2. So that also CD would also be inverse proportional to the thickness of the boundary layer, theta, right? Okay, the final question is, we have one additional parameter nu here. If you increase or decrease nu while keeping the same UE, same thickness, how would the dissipation increase or decrease? Right, we're just defining d as this. It's proportional, right? So okay, so CD would be proportional to nu divided by UE divided by theta, which is like 1 over Reynolds number based on theta. Okay, so let's say UE cube times something that scales like 1 over we have something 1 over RE theta, so the Reynolds number based on theta, okay, times RE theta times CD. So this whole function RE theta times CD, that is basically makes this CD to be able to be modeled as a function of h. All right. So this I theta times CD would be we can choose this just as a function of the velocity profile from the, let's say, Faulkner-Scan family.
How do you know it's a function of H?
So remember, like any member of the Faulkner-Scan family can be parameterized either using lambda or using H. Right, so as you change the, or as A, right? So basically you can choose any of these monotonic parameters as a parameterization of the Faulkner-Scan family. So in the Thrice method, we chose lambda, and in this method, H is in the two equation. This is the two equation method. Basically, we are solving for theta and solving for theta star, right? In this two equation method, H is the most common choice. Okay, so basically the method would be solving for theta and solving for either theta star or the ratio between theta star and theta, which is basically H star, right? By combining these two equations, and H star is a function of H, CF is a function of H, and D is a function of H. That means everything can be written as a function of theta and H, which are going to be the independent variables in this calculation. So you can, for example, you can basically the equation for theta is going to be very clear, right? Let me see. D theta dx is going to be half of CF, which is going to be 1 over RE theta times TH. So this whole thing is CF. Minus theta over UE times 2 plus H, right? So delta star is equal to theta times H, dUE dx. So this is going to be the equation for theta. And then again, we're going to have an equation for H. So dH dx is going to be, first of all, we want to translate it into an equation for H star. So basically, because we have the relationship, we have a model relationship between H star and H. So this is going to be dH star times dH star dx, right? And this can be computed also from the Faulkner-Scan family of solutions. And then dH star dx can be modeled as, so because H is equal to theta star over theta, it can be modeled as 1 over theta times d theta star dx, right, minus theta star over theta squared d theta dx. So d theta dx already have a formula, a closed formula, and d theta star dx has a formula that we just derived from the energy equation. And the only unclosed term in the d theta star dx is actually this d, which again we model as a function of H by looking at the Faulkner-Scan family of solutions.